So this is Lab 2. We're going to be talking about and taking a look at different types of likelihood functions. And by different types, I mean sort of generically how we will handle and view and deal with parameters in a likelihood function. And not sort of, and not which model are we going to look at. And likelihood functions, you've already gotten a hint, are very important. They're going to show up in lots of different contexts, but they're also may have multiple parameters, and we need to know how to handle multiple parameters when we focus on one and are not so interested in the other. So we'll just jump right into it and get started here. Let's say I have a bunch of observations, and they're independent, identically distributed from this distribution. And this distribution has got two parameters, theta, and capital theta is the parameter space for that, and gamma, and capital gamma is the parameter space in that case. So for example, if this were a normal mu sigma squared for my model, you might have mu might be an element of the reals, right? Meaning it can go from minus infinity to plus infinity. But sigma squared has to be positive, so that's the reals plus or 0 to positive infinity, right? So that's the idea. That's what these spaces are. And the likelihood function, of course, emphasizes the parameters over the data. So if we turn this into a likelihood function, we get capital L of theta gamma given the observed data. Notice that's a lowercase x. And that's proportional to this likelihood function here. Here I'm using this vector notation for the data. Since everything's independent, it's just the product over all the individual xi's. And what we're going to assume is that the parameter of interest, the thing we want to learn about, is theta. And there's another parameter. And we're going to need to know what that parameter is to be able to do some computation. But we're not really interested in it. I just need it so that I can learn about theta. Well, that extra parameter is called a nuisance parameter. So gamma here is a nuisance parameter. And ideally, in order to learn about theta, I'd like to have, say, a density. Well, actually, let's write it like this. I'd like to have a likelihood function that depends on the data and will tell us about theta, but there's no gamma in there, right? Because I don't want to have to specify gamma. I don't know what it is. If I pick something wrong, I could learn different things about theta. And so I'd like to get rid of that if I can. So ideally, I'd like something like this. And we drew in class a couple of these functions where L was over here and theta was over here, and we looked at this distribution. Now, of course, we, with two parameters, so when you have L of theta and gamma, you might have theta here, gamma here, and then of course you get contours. I'm going to just change the color. And so you might have a contour plot here for your likelihood, because your likelihood's not one-dimensional, it's two-dimensional. And in here is your maximum point here. You know, that might be theta hat, gamma hat. Okay? And so rather than, so the problem with a two-dimensional likelihood is that it's hard to deal with. How do I learn about theta, right? Well, at this gamma, if I were to take a particular slice, you know, that particular blue slice, I'm going to draw over here, might look like that. Well, suppose I wanted to take another slice. Let's pick a different color. Suppose I take this slice here. Well, that slice may look like this. So this is when, you know, gamma equals gamma prime, and this other one And actually, we can just go ahead and use the same color. This other one would be, say, gamma equal to, say, gamma star. So this is gamma star, and then the green, of course, or purple rather, I'm sorry, and then the purple, of course, is gamma prime. And so you take different slices of that, you learn different things about theta. And so you need to have the quote-unquote correct gamma to learn properly about theta. Well, so how's that work? And so that's what we're going to talk about today, is ways of getting to the right or to the gamma that we want. So let's shift this up and let's be specific now about what are the types of likelihoods that we're going to look at. The first and the easiest is to just integrate over gamma, and that's called a marginal likelihood. And here I've done LM to just emphasize it's a marginal likelihood. For the purposes of our lab, in practice, people just use L and L of whatever, and then it's up to the user to figure out what type of likelihood we have. So here's the marginal likelihood, and this is a density, right? In this case, this is just a density of the data given theta, but there's no gamma, and there's no gamma because I actually took the joint density, well, not joint density, I actually took the density that depends on theta and gamma, and I integrated over a prior for gamma. So if in fact you know a prior, you can integrate it over, and that's called a marginal likelihood. This is, of course, a very Bayesian thing to do. I shouldn't really say Bayesian, it's just a very natural thing to do, probabilistically. And now, if in fact gamma takes certain values according to G, then I will in fact get the right inferences about theta. If I use, if gamma, for example, were distributed H of gamma, and I used G, then this F is not going to be the right F, right? So there's some sense about, okay, gamma needs to have a distribution, and it's got to have the quote-unquote right distribution for you to be able to get the right marginal inference. We do lots of marginal inference in statistics, and we'll see it as we go through class. The estimated likelihood is probably the most frequently used, and it's the easiest. What it says is you take the original density that you had that was a function of theta and gamma, and you're interested in theta, so you're just going to plug in a guess for gamma. Well, what would a guess be? Well, a guess can be anything, any estimator of theta. And so here what I've done, don't forget our likelihood, right, is this. Right, given all the data. So now what I've done is I've just added the hat here. So I'll make that guy make a guess. A lot of times this is, we plug in something called the global maximum likelihood estimator, or the global MLE. And I'll give you an example of that as we go through. Estimated likelihoods can be good, they can be bad. It turns out that they're often have a little bit more variability than you might like, and it really depends on how good an estimate you happen to pick for gamma. Another approach that was not as favored earlier on and now is tending to be more of a favorite as people come to like it and see its properties is to do something called a profile likelihood. Now, a profile likelihood is conceptually, I think, not too hard, but it's very useful in practice. So the idea of the profile likelihood is to say, okay, look, let me write down my likelihood function again. So here's my likelihood function, and I need to get rid of gamma. Well, I can plug in the global MLE. Right? So I could just take the max over all gamma. Okay? And if I just did that, then that actually is going to turn out to be that thing up here for the global MLE. All right? Here now I want to do something different. So I'm going to take the likelihood for theta, gamma for x. All right? And I'd like to take the max over all gamma at each theta. And I don't have a good way to write this at each theta. And so the way we usually write this in the notation is we say L of theta, give me the maximum likelihood that depends on that gamma, and do this. All right, and that's basically the idea of the profile likelihood. And here, the idea is that for every theta that you look at, you're going to find the best guess of gamma. And if theta is 1, you'll pick the best guess of gamma. If theta is 4, you'll pick a different guess of gamma because that will be best. And I'm going to illustrate this, and we have one very good example to help illustrate exactly what's going on here. And I think it's important to learn. One way to think about this is if, in fact, so let me draw. I think it's helpful to draw a picture here. I'm going to draw a picture of a two-dimensional likelihood. So here are my graphs, and I'm just going to let this be theta here and this be gamma here. I'm writing all over this, but that's okay. And again, we have these contours, just kind of almost like you might see for bivariate normal distribution, right? Where the likelihood is going up as you go up these contours. So here, the likelihood might be 1 over 100. And here, the likelihood might be 1 over 50. And here, the likelihood might be 1 over 10. Okay? So you're going from small, going up the chain, and you're getting bigger and bigger and bigger and bigger and bigger, et cetera, et cetera, et cetera. Okay. And so in here is a point, right? And that point here is at theta hat, gamma hat. Those are the maximum likelihood estimators over all points in this square. Now, we talked before about how we took these horizontal slices, but suppose I took a slice right along the maximum here. See this purple? Right along the maximum here. And so what is this? This purple line happens to be the largest likelihood, okay? So this is the likelihood of theta and gamma where L theta gamma is a maximum. It's literally this thing here, okay? And what you can see is you can say, okay, this at this point, right? For this gamma, that dot is the maximum. For this gamma, this is the maximum. Okay? For this gamma, this is the maximum. And so this purple line, if you were to draw that purple line looks like this. And that is called a profile likelihood. Okay? So the profile likelihood is taking not a horizontal slice, but a diagonal slice. Essentially, it's the ridge of a mountain. One way you can think about this is if you're looking at a mountain straight on, you'll see the profile of the mountain. Just like if you shine a flashlight or a bright light against the mountain and you were to look at what it looks like against a wall, you'd be seeing its profile, its projection onto the wall. And you lose the depth of the mountain, but you see all the high ridges and the high peaks. That's what that profile likelihood is. And that's one of the reasons it behaves well. And so we'll go through and see some examples. The last one that we're going to see, and we won't see it right away, but we'll see it later on, is called a conditional likelihood. And sometimes you can find a statistic, a sample mean, a variance, something interesting in the data, that if you condition on that statistics, gamma falls out of the likelihood. See, there's no gamma here. There's just theta. And this statistic takes the place of gamma. It's actually called a sufficient statistic. So S is sufficient for gamma. And this idea is key for analyzing 2 by 2 tables, and we'll take a look at that when we get there. But so this is another approach. All right, so we're going to see examples of all these, but I thought it would be best, let's take a look at the two we will most often see. And so let's take a look at the profile and estimated likelihood under a normal model. So here your data are normal, mean mu, variance sigma squared, and for simplicity I'm just writing all the data as a vector here. And so the joint distribution of the data is, in fact, this likelihood that everybody knows and loves, right? 1 over the square root of 2 pi sigma squared raised to the n, et cetera, e to the sum of squares over n minus over 2 sigma squared. Now, I'm going to want to maximize this thing, and I want to know what, for example, first thing that we could do is find the maximum likelihood estimators for mu and sigma squared. And we did this in the class notes, but we'll do it again. So you take the log of the likelihood. Notice here the capital L gets changed to a lowercase l, right? So that's the log of the likelihood. And you take the log, and then you drop things that, parts that you don't need. So you don't need this 2 pi, right? Because this is going to be log 2 pi plus log sigma squared times n over 2 minus, so that goes away. And you're left with just the key things. And you want to find the maximum likelihood estimator, so what do? So you take the derivative, and you set it equal to 0. Now, in this case, we know that the MLE for mu is the sample mean x bar. And so we also happen to know that the MLE for sigma squared is going to be the sum of the xi's minus mu squared over n, because we had just talked about that in class. And so the way you do that, of course, is you take the derivative with respect to the likelihood, or with respect to the thing that you want to maximize. So here we're maximizing the variance. I've done that. And then I'm going to set this equal to 0 and solve for sigma squared. And I get this answer. What's interesting about this answer is this is the point before I plug in mu equals x bar, because I don't have it, but I don't want to plug it in yet. This is actually the pure form of the maximum likelihood estimator, and it's a function of the other parameter. And when you go find the global solutions, you plug each solution into each other because it's a system of 2 equations and you're trying to solve it based on the data. But when you're doing a profile likelihood, you don't do that. You just leave it as is. And so sigma square hat, your estimate of the variance, depends on mu. That means if mu is 0, you're going to get one estimate of the variance. If mu is 10, you'll get another. So what you're literally doing is finding the best estimate of the variance for each and every mean that you're considering. Sort of like a tailored fit likelihood. It gives you the best you can given that I know you're interested in mu. And I'm going to take this, okay, and I'm going to plug this back in to the likelihood here and here. And that's going to be my profile likelihood. All right, now I can mess around a little bit with the sum of squares. So because the sum of, I could use a space here. Because the sum of xi minus mu squared, I can break this up into these 2 pieces, sum of squares pieces. And then you can reduce things. And so here's mu, and here's the new variance. And notice that depends on mu too. So I can just write this as a function of mu. And to remind people that it's a profile likelihood, I put a little p there. And I've plugged it in, and then I eliminate some terms, and you just get left with this simple expression. It's sigma hat squared minus n over 2. And this sigma hat squared, by the way, sigma hat squared is equal to sigma hat squared times mu. I've just dropped the mu notation. That is some ugly scribble up there, so we can make that look nice. All right. And then I've done a little algebra, and I've broken up the sums of squares here. I've divided through by a piece. I broke it up again into certain pieces, and I made it look like this kernel because that's the kernel of a t-distribution. And in fact, here you have t squared, and this t squared right here, this t squared is this thing right here, which is a z squared actually. This is a standardized statistic squared. So in fact, what we find is that the profile likelihood for the mean, okay, that's this thing. This is the profile likelihood for the mean. That is proportional to a t-distribution. So when you don't know the variance and you profile out, basically you get a t-distribution. And that should be very reassuring. Now, an estimated likelihood is going to be different. An estimated likelihood, you just plug in the global maximum likelihood estimate. Well, what would the global maximum likelihood estimate be? In this case, the global maximum likelihood estimate is going to replace mu with x bar. So it's going to be the sum of the xi minus x bar squared over n. And then sometimes people might even want to have n minus 1 in the denominator, which is what this guy is right here. So I can just plug in an estimated likelihood. Just plug in the sample variance. See how that goes. All right. So one simply plugs in a fixed estimate for the estimated likelihood. That's this E here. Didn't mean to do that. And the difference, okay, is that the profile likelihood is finding the best guess for the variance at that particular mean. So the profile likelihood, because it's so tailored, often ends up being a lot more flexible and giving you more accurate estimate of the variance, whereas the estimated likelihood, it assumes you know the variance and that the variance is actually s squared. The variance is never going to be exactly s squared. If s squared is close, then you gain a little bit, but if s squared is far from sigma squared, then you can be way off. And so the profile likelihood is nice and flexible, kind of adjusts your likelihood as you go through. All right. So that's Lab 2. I am now going to go in here and inside the Dropbox folder, you will see some examples. And so it's in this code SF file. So I'm going to tap on that. And I'm going to draw these likelihoods for you so you can see, and we'll talk about them, and then we'll end. So in the normal example, suppose I know the variance, okay? Here's the normal example, and suppose I know the variance. Well, then my likelihood is just the plain old likelihood. I can plug everything in. I can plug the data in, and I can plug the variance in, and I get a likelihood. The problem is that likelihood will be wrong if I don't know the variance or I guess wrong. So I can use the data to estimate what the variance is. And actually, let's do this. And so now, basically everything depends on the data, okay? And so that's what I have plugged in here, right? The profile likelihood, all I need to do is give it the data, okay? I don't have to give it s squared per se, although s squared you can compute from the data. So this is a little minor distinction. And it will go calculate what the variance is. So for here, for the variance, it's using this. And then to just show you the difference, this last case is a marginal likelihood. So this is a marginal. We looked at the profile and estimated, and this is a known likelihood. For the marginal likelihood, I'm going to assume I have a prior distribution, which is inverse gamma for the variance. And since my likelihood is proportional to this, which we have done already, t-distribution, it's actually pretty easy to just put the inverse gamma on. And so this this extra PDF. I should say the code to run this, to compute these, is in the Dropbox. There's a sweep. I believe there's a sweep file. But let's take a look at what we have. And so for each of these cases, I drew some examples, and then we're going to compare them. So for the case one is just the plain old likelihood, assuming you know know the variance. And so when n is 10, we happen to be shifted over a little bit, 100, 500, and 10,000. And of course, this is the behavior we would expect. Here I've set the mean to be 10, and so you have this sort of convergence of the MLE, moving the center of that in, but also the width of that likelihood is getting skinnier and skinnier. Case 2 now, if we go back, I believe this was the estimated likelihood, and we're going to plug in an estimate of the variance. And so here we're plugging in S squared for the variance. Here we're plugging in S squared. So we plug that in, and that doesn't look too different, although it's hard to compare directly. In this case, this is the profile likelihood right here. And this is the marginal likelihood. But of course, to do the marginal likelihood, to do the averaging, I need to specify my prior distribution. So that's what I have done here with alpha and beta. And so I think you can compute these and you can look at them, but they're very hard to compare. So I'm going to pull them all together on one graph. So here I've changed for the marginal likelihood what the parameters are. So here you can see now with alpha 0 and beta 10, you get a much wider place to start here, with 10 observations. And here you get much narrower over here, okay, with alpha 10 and beta 0. You get much narrower. So you're adding a lot more information to the data. Both of these are using the same 10 observations than you were with when alpha and beta are equal, which is a little bit more of a flat prior, less information. So that's why these black lines here, that's why these black lines look pretty close, is because this prior is not too informative. And you can see how it changes depending on what the prior parameters are. You can have less information, because you have a wider likelihood. So there's more means under the hump here. And here, this is saying, oh, I'm more precise. I know your mean is only in here. So now you have more information. But the rub is that they come from the same data. All you're doing is changing the prior. So you get roughly the same point estimate, but you get different variances. And again, it's hard to see this from the way this is drawn from figure to figure here. And so let's put it all in one figure and take a look. And that's this last figure right here. I'm going to shrink this down so we can get the whole thing. So here is the case for 10 observations. And we're using the same 10 observations, and I'm going to apply each technique. And so let me get here. And so this purple, let's start on the outside and work our way in. This purple here is the marginal likelihood. That's this guy here. And giving a little different information, so you get more variance. The marginal likelihood with even more information here is the green. That's this guy on the inside. So we have the two limits here. One where I've increased the variance and one where I've decreased the variance, but notice their estimate of the mean is the same in this case. Okay, so you're all playing with how much information you have. On the inside, there is a likelihood on the inside, and it's this blue one, actually, this marginal distribution. That's this blue one. You can see it right down in here, right? And that's not too different from the others, okay? And this is the one with the, what we say, flat prior or non-informative prior. So it shouldn't be surprising that that matches the other approaches too much. The black line, which is harder to see, which is in here, that's this guy right here. That's the where you just assume you happen to know what the true variance is. So that's our target. That's the fixed variance. That's what we're trying to get close to. And then the red, okay, is the estimated sigma, which means you just plugged in S squared. And then this gray line, this sort of light gray line, I guess I'll use a different color now. This light gray line here, that is the profile likelihood, and you can see it does what profile likelihoods do, which is it's conservative in terms of information relative to the other approaches, saying you have a little bit more variance. And so all these approaches, if you wanted to come up with, say, a confidence interval, you would probably do something like this across the way. And the intervals that you get now are going to be very different. So this is your green interval in here. So this would be your confidence interval from that model. Your confidence interval from this other model here is really wide, right? It goes from this point to this point. And everything else in here is pretty close. So everything else in here would give you basically this. I'll scroll down here as your confidence interval. So it matters how you plug these parameters in and how you change them and what you do with them. So I'd encourage you to draw a few of these. The formulas are here, the R code's there. Play with the parameters, plug in different data, and get a feel for a little bit of what you're doing. Because as we go through the course now, we're going to have to keep track of what parameters we're interested in and what parameters are nuisance parameters and how we handle them. Okay, thank you for your attention.